So the first half of question 5 is a pulleys question. So we have a block P and we know its mass, and we have a block Q and we know its mass, and they're on a rough surface, which means that there is friction. They're connected by a light and extensible string, which goes over a smooth fixed pulley. Block Q is on a horizontal surface, and block P is on an angled surface, and the angle is 25 degrees, as shown in the diagram. The coefficient of friction is 0.2 between the blocks and the surface, and they begin to move when they're released. So we're instructed to show on separate diagrams the forces acting on the blocks while they're moving. So we'll start off with P. So of course we're going to have the weight, which is mg, and we know what m is. It's 6.3 for block P. So we can write 6.3 g. Now we can resolve this as well to be parallel and perpendicular to the inclined plane. So if we have a think about this, so first of all, let's have a look at this right angle triangle for now. So this angle here is 90. That means this angle is 90 minus 25. And then the full angle here, this one, is 90. So you have 90 minus 25 and something will give us 90. That means that the angle here has to be 25. So that means that here we're going to have 6.3 g cos 25. And here we're going to have 6.3 g sine 25, sorry. Now, of course, when P pushes down on the surface pushes back up on P. There's a reaction force. The string will apply force to P, tension. And we are also told that there's a force of friction. Now, for block Q, there's also its weight, which is mg. And we know that m is 2.5 for block Q. So this force is 2.5 g. There's going to be a reaction force upwards as well. And we're going to have the tension in the string pulling it this way. And since it's moving to the left, the friction is going to be going to the right. And in case it wasn't obvious for the other one, because it's sliding down the slope, the friction is acting up the slope. So now while we're here, we may as well calculate the friction. So for block P, the reaction force will be equal to 6.3 g cos 25, because it's not moving in this direction at all. It's not moving in this direction, which means that these two forces must be balanced and equal. So you can say that R equals 6.3 g cos 25. And we know that the friction, the force of friction, that'll just be mu or, which is mu is 0.2, and or is 6.3 g cos 25. Put that into the calculator, and you get about 11.191 newtons. I'll do the same here. So here the reaction force is just going to be 2.5 g because it's not moving up or down, so they have to be equal. So or equals 2.5 g. And remember that the force of friction equals mu or, which is 0.2 times 2.5 g. That's about 4.9 newtons. Well, it's exactly 4.9 newtons. So part 2 asks us to calculate the acceleration of the blocks. So we're going to have to come up with an F equals ma equation for each of the blocks to kind of relate some of the quantities together. So we'll start off with block P. So we can say F equals ma. And we know that m is 6.3, so 6.3a equals, and we'll take left as positive, so just because they're both moving to the left. So we'll say 6.3 g sine 25, because as you can see, that's the force that's pushing it down the slope. And then take away from that the tension and the friction, which is 11.191. Now for block Q, we're going to have ma, and m is 2.5, so 2.5a will be equal to the tension is pulling to the left, minus the friction, which is 4.9. So 6.3a will be equal to, now 6.3 g sine 25 minus 11.191. That's about 14.901. Then minus the t. And then here we can isolate for t, so we can sub it into the other equation. T equals 2.5a plus 4.9. Let's put that into this equation. So we're going to have 6.3a equals 14.901 minus 2.5a minus 4.9. So it's going to be 8.8a equals 10.001, which means that a equals 10.001 all over 8.8, which is approximately equal to 1.136 meters per second squared. That's to 3 decimal places. So that's the common acceleration of the two blocks. So part B was a uniform motion question. It's a pretty long one, so we're going to take it bit by bit and write down each bit of information onto a graph. So we have a Monday and we have a Tuesday. So on Monday morning, she starts her car and accelerates uniformly for 40 seconds to a speed of 22.5 meters per second. So her car starts at rest and speeds up to 22.5. And that takes 40 seconds. So of course this is a velocity and this is time, velocity time graph. She travels at this speed for 8 minutes, so we can draw in that little horizontal line. Then 8 minutes in seconds is 480 seconds. And then she decelerates uniformly to rest at work. So then she slows back down until she gets to work. And we don't know how long that takes, and we don't know the rate at which she does it. But we know the time will be 8:30 when she gets there. Now on Tuesday morning, she leaves her house 140 seconds later, and she takes the same route, so that means the distance is going to be the same. She starts her car and she accelerates at 1.5 meters per second squared for 20 seconds. So we can calculate her speed by the end of that. So remember, acceleration is just going to be the slope, the rise over the run. And we know the run, well, the run is the horizontal, and that's 20 seconds, because remember, the horizontal, the x-axis represents time. So that's going to be A is 1.5 equals the rise is basically just the velocity over the run, which is 20. So 20 times 1.5. This means that V is equal to 30. So once she gets to here, she's going at 30 meters per second. She maintains it for 6 minutes. So 6 minutes is 360 seconds. And then she decelerates uniformly to rest. And again, we don't know how long that takes or the rate at which she does it. But we know that she'll get there again at 8:30 exactly. It's also important to point out, if they asked for accurate time velocity graphs, this wouldn't suffice because these are drawn the exact same just with different numbers. You'd have to make sure they're all in proportion if they asked for an accurate graph. And they'd probably give you a place to draw the graph as well, so it'll be fine. So now there are two things we need to look at. We need to look at the time taken and the distance traveled, because they're the two things we know about. So we're going to look at the time taken first. So we know on Monday morning, so she accelerates for 40 seconds, plus 480 seconds, plus this time here, which I'm going to call T1, for the deceleration period on Monday, plus T1. And we know that in total will give us capital T, which is the time taken for her to get to work. The total time taken for her to get to work. Or in other words, capital T, the time for her to get to work is 520 plus T1. Now if we look on Tuesday, well, it's going to be the total time taken minus 140, because she leaves 140 seconds later, which means the total time she spends traveling to work is 140 seconds less. That's going to be equal to 20 plus 360 plus T2 is what we'll call this final time here. Now if we just rearrange bringing all the numbers to the other side, we get T equals 520 plus T2. Now if we have a look at these two equations, you could sub them in, which means 520 plus T1 equals 520 plus T2, or in other words, the big takeaway is that T1 is the same as T2. That's the first big fact. T1 equals T2. Now the second fact is that the distance she travels, it says she takes the same route, so the distance she travels is going to be the same both times. So remember, distance is the traveled is the area under the curve, so we can just calculate the area of each of these shapes. So the first shape here is going to be a half times the base times the height, which is 22.5 times 40, plus, and then we have a rectangle, so that's going to be just base times height, which is 22.5 times 480, plus, and then a half times 22.5 times T1, whatever that is. So we know this will be true, the distance traveled is the same. We know that T1 equals T2 as well. So let's just simplify the rest first. So that first term is going to be 450. Second term. And for this last one, T2 is the same as T1, so I'm going to write 15T1. So now we can solve for T1, and then we can divide both sides by 3.75, which means that T1 equals 40. So what does this mean? Now we got to take this back to the context of the question. So we know on Tuesday, the total time it took her to get to work was t minus 140. That's how much time it took. And that was equal to 20 plus 360 plus t2. And remember, t2 is the same as t1. So to find out what the total time minus 140 is, we can replace that t2 with the t1, which is 40. So that means that the total time minus the 140, because remember, she left 140 seconds later, which means it took her 140 seconds less than it did on Monday. That's equal to 420 seconds. So that's the time it took her to get to work on Tuesday. So we can convert this to minutes by dividing by 60. So that's equal to 7 minutes. And remember, she arrived at 8:30. So take 7 minutes away from that. That means she left her house at 8:23. And that is the answer.